Hi everyone, my name is Yasaman Nemati. I'm a second year PhD student at Laval University. I work under the supervision of Professor Dupuy, Quencel, Giroux, and Smith. My thesis subject is assessing the geophysical attributes of hydrothermally altered gold deposit using petrophysical logs and geochemical analysis. So these are the list of our partners in funding and research. So you see a cross-section of the area that we are working. So we are working in the Rouyn property, which is located in the Superior Area province, and it spans 12 kilometers along the Cadillac-Lardell Lake break. This area has been hydrothermally altered, and the host rock that has experienced this hydrothermal alteration is the Piche layer. The main composition of the Piche layer is the schist carbonate. And as you can see, in our western part, we are having more endowed areas, and in our eastern part, we are seeing less endowed areas. So last summer, we gathered the geophysical information from 7 wells in the area, and from these 7 wells, for 3 of them, we have their geochemical analysis. So the objective of my project is to, first of all, we would like to compare the geophysical signatures from the altered area and from the endowed area and the least endowed area. And we would like to see and understand the effects of alteration on our geophysical signatures. And later, we would want to check the possibility if it's possible to establish a relationship between the geophysical signatures, alteration, and the gold endowment. So in order to be able to do that, we need to make a connection between geophysics, geochemistry, and geology. So we know that it's a matter of a scale. So we know that the elements, they form together and they make the crystals. The crystals, they group together and they form the minerals. When we are reading the geophysical information, we are reading the geophysical characteristics of the minerals. However, the minerals can have variation between their composition, and there are some events that can change these composition. So just like alteration changes the minerals. So it means that it changes the elements. The elements are moving between the crystals and within the minerals. So in order to be able to assess this information and these changes within the geophysical aspect, we need to be able to establish this relationship between the geology, geochemistry, and geophysics. So one tool that can really help us to understand the effects of alteration is the mass balance. The idea of mass balance is easy. It says that the mass of the altered rock and the unaltered rock should be the same, but in reality, it's not. So it means that within the alteration or because of the alteration, there are some mass gains and some mass loss within the rock. So if we can somehow understand these changes in mass, we can relate it to the alteration, and we can relate it to the movements of the elements within the altered rock and the unaltered rock. So for doing the mass balance, we use this formula. Basically, in order to be able to use this formula, we need the concentration of the elements within the protolith or the unaltered rock, and also within the altered rock. And also we need to find and select the immobile element during the alteration. So our geochemical data were not evenly distributed. We had a lack of data for some parts, and they didn't have any normal distribution. So we used a statistical method named bootstrapping. Basically, bootstrapping is a statistical method, a statistical resampling method that chooses data with replacement from the original data. And if you do it just like thousands of times, like 5,000, 10,000 times, at the end, you can have a normal distribution for your sample weight. So also, we wanted to see which elements are varying together, which elements are covariating. That's why we use the PCA. The PCA is a method that can help us to reduce the dimension and also find the elements that are moving together. So for doing the PCA, you select the axes that it includes the highest changes in the data, in your data, and then you select your data in this new dimension. So for doing the mass balance, as I said, we need the composition of the protolith. As I said, our host rock for the hydrothermal alteration is Piche, which is composed of the carbonated schist. So its protolith version has been the komatiite, but we didn't have the composition of komatiite for our area. So we searched in the paper and we gathered some information from the different Archean cratons in India, Africa, and Australia, and also from the Superior province. And we realized that their compositions are not changing so much. So the highest changes, the highest deviations actually was for the silicium and magnesium. And if we consider that some of these Archean cratons are more mafic than the others, so it explains well that why we are seeing these changes. So yeah, we need to find the immobile elements also in order to be able to do the mass balance. So we gathered the geochemical analysis from 320 wells in the area, and we assessed the rare earth elements, which are the elements that usually stay constant and they do not move during the alteration. And within these elements, we found that the zirconium and hafnium shows the most linear relationship. And as our 3 wells, which we have logged geophysically, we didn't have that much of hafnium, so we chose the zirconium as our immobile element. So we did the bootstrapping and we calculated the concentration of altered version and protolith version for each element. And the plot that you're seeing is showing the values with the 95% confidence limit. So we realized that for this well, which is our Gamble well, our geometric means best value is around 58%. So it means that other elements, depletion or addition for this well should be compared regarding to this value. So this is the same plot, but showing as the box plots. So we did the mass balance for each well. So based on our calculation, we realized that our Gamble well is losing mass. However, our Agmito and Astoria well are gaining mass. So these are the results per elements for the Astoria. As you can see, we are gaining barium, strontium, copper, vanadium, and other elements in our Astoria wells, and we are losing some of them in this well. However, it's not really easy to interpret this plot. So we would like to see the elements that are moving together and they are covariating. So we did the PCA and we suggested and selected some groupings for our data. For these groupings, we also take some ideas from the Hood paper, which he almost did the same kind of mass balance for another hydrothermally altered gold deposit. So for our elements, we found the potassic elements related to the potassic alteration, to the sodic alteration, elements related to the carbonatization, to the mafics, and there are some elements that are more related to the immobile. So these are the mass balance results per groups that we found. So we can see that in our Gamble well, we are losing some of our mafic elements and also some of our elements in the carbonatization group, but we are gaining them in our Astoria and Agmito. Also, we can see that we are increasing and gaining mass for our elements in the potassic alteration group and the sodic alteration. So it means that our rocks in these 3 wells, they have experienced the potassic alteration and the sodic alteration. So now we would want to relate these results of the mass balance and geochemistry to our geophysical information. So this shows a section, Piche section of our Agmito well. So in this well, our Piche has many different sections. The golden colors, they are showing the schist carbonated schist parts, and the purple ones are showing the carbonated schist fuchsite parts. So for these different sections, we plotted the calculated mass potassium gain, and also we all plotted the gamma ray reading and potassium reading from the geophysics. So as you can see, the potassium reading and from the geophysics, and also the potassium gain from the mass balance, they completely correlate to each other. So we are seeing the same trends for them. Also, we are seeing the same trend for the gamma ray, except for this third section of the Fuchsite part. So as we check the geophysical signatures in this part, we realize that, okay, because the gamma ray is composed of the potassium, thorium, and uranium, the values of thorium and uranium has decreased in this part, and that's why we are seeing a decrease in gamma ray, but not in the potassium. So what about the other geophysical signatures? So we chose two different sections from the Fuchsite part in the Agmito well, and they both have the same the length of 4 meters. So we had enough geochemical data for these two sections, and we did the mass balance for these two sections, and we would like to compare their geophysical signatures, average geophysical signature. As you can see in the second part, we are seeing a decrease in magnetic susceptibility in specific parts. And as you can see, the average value for our magnetic susceptibility in our second part is lower than the first part. And as you can see from the mass balance and the geochemistry, we see that we have a loss of iron in the second part, and we have a gain of iron in the first part. So we know that the mass balance, the magnetic susceptibility is highly related to the magnetite in the rock. So when we are decreasing or when we are destroying our magnetite in the well, so we should see a decrease in our magnetic susceptibility. So if our theory is correct, so we need to be able to see the same trend in our other geophysical signatures. So as we compare the density, we realize that the density in the second section is lower than the first section. And also the velocity follows the same trend. The second one is showing the less velocity for the P wave than the first one. We also expect to see the same trend for the spontaneous resistivity. So we expect that as our iron, as our magnetite is getting destructed, we need to see an increase in our resistivity. However, we see that in our second section, we have a decrease in the resistivity. So what can it be? So we need to check on our other geophysical data. So if we look at our IP lines, we see that for the first part, we are seeing a straight line. So it means that they are not changing. It doesn't show anything. However, in our second well, in our second section, we are seeing that our IP data is changing, and its average values are higher than the first part. So it means that there's a polarizable element in here or mineral in here that is giving these responses to the IP. We know that pyrite and arsenopyrites are two of the elements and two of the minerals that can have a very good and strong IP responses. So when we check the information gathered by the geologists, we see that in the second part we are we are having a higher mineralization of pyrite and arsenopyrite, and this goes well with the idea that we are having an increase in the IP and the decrease in the resistivity. So what it means that we had the magnetite mineral and magnetite crystals in our komatiite, but because of the hydrothermal alteration, this magnetite has been destructed, and it has reacted with the fluid, and it had gathered, it had formed the new pyrite and arsenopyrite minerals, and that's why it deposited the gold, and it deposited within the veins of the rock. So this explains the theory why we are seeing this decrease in the spontaneous resistivity. So for our future steps, right now we have done the mass balance for each well and for each section of the Piche layer. However, we are going to do these mass balance calculations for each point of our data and each depth, and we would like to see and relate their geophysical signatures to the results of the mass balance to see to further interpret them. this is the list of our references, and thanks for your attention.
Great, thank you very much. We do have some time for questions.
Yes, thank you very much for that very interesting presentation. Could you go back to the slide showing the principal component biplot, please?
This one?
Yeah, yes, that one. Now, the data that were used, were these residuals, or were these the actual values expressed as proportions, parts per million?
These data are all, they are all the percentage of each element. And
Okay.
They are the readings exactly from the geochemical analysis, not the mass balance.
Okay, so a couple of issues here. First of all, you're using the values expressed as both percentage and parts per million. So you've got a scale
they are
difference.
all in person. Yeah, you're right.
Okay, and the other thing is that there is the potential problem of closure here, in the sense that because these are compositional data, they are actually not independent. When one value changes, by definition, the other must. So have you considered looking at log ratios as a way of examining the relationships?
Yes. Well, as I said, I followed the steps of the Hood paper. So yeah, we need to compensate for the closure problem. So what we did is that we transformed this data to a log ratio, and we divided them by their geometrical means. So these data, they do not have the problem of closure. Yeah.
Okay. Well, it would be helpful to show that because that was certainly a question I had when I saw that.
Yeah. You're right. Thank you.
All right. Thank you.
Thank you.
Very good. Matt, you have your hand up.
Yeah, I'm just wondering, excellent talk, and following on, I guess, from your one last year, but I think we and you may know this, but we actually completed a few holes around Cinderella, and I can see that you have, there's a bit of a gap on the long section there, your first slide.
Yeah, we didn't have the geophysical signatures for the wells in Cinderella. No, that's why we didn't do the mass balance right now for them, because we wanted to relate the result of mass balance to the geophysical signatures.
Okay, but you're aware of those new holes?
Yeah, I know that there are some.
Yeah, good.
Lots
Okay,
of
great.
there, yeah.
No, just letting you know in case it wasn't too late to add one in the middle there.
Yeah,
Thanks.
thank you so much. Yeah.
No problem.
All right, anything else? Mike Lesher's put a couple of comments in the chat room. You may want to have a look at to maybe good for your alteration. Are there any other questions, comments?
Yeah, Ross, I have a quick question.
Yeah.
Sure do.
The amount of graphite in the rocks is looking to be very important when we try to interpret the magnetotelluric conductors. And I wasn't able to follow well enough all your analysis to know whether you're able to analyze carbon in there as an element, and in what form that would have.
I guess this also answers the questions in the chat, that, well, we didn't have the geochemical analysis for all the elements. So, I mean, we did the mass balance with the elements that we had their information. So we didn't have the geochemical analysis for the carbon, for example, or the thorium. So we did the thing that we could with the data we already have. So, for example, I didn't have the information of carbon or thorium. But as I also checked the composition of the komatiite or the other rocks, I realized that the carbons, I know that they exist in the rock, but they're not the main components of the rock. So that with this justification, I did the mass balance.
Okay, thank you. And I know that the Geological Survey of South Australia has a big core lab that they're doing hyperspectral analysis on a micro scale on a lot of core. Is that method able to see small amounts of carbon and graphite?
I haven't heard, I haven't read about that method that you're saying, but as I said, right now we have done it for each well, and we have done it for each section of the Piche within each well. We are trying to do it for each line of the data. I mean, each point and each depth of the data that we have. So we hope that we can see it in our geophysical responses, because, you know, the geophysical responses, their precision is really high, because we have gathered our geophysical data in just like, you know, the centimeter by centimeter. So it's really precise, and I hope that we can see, we can correlate them very well together.
Thank you.
Thank you.